Okay, so this second video here, I'm going to go back and draw my little silicon PN junction, or really what it is a diode. And so we've got my P region, my N region, and then we talked about how I've got this depletion region set up with some minus charge here, some positive charge here. Okay, so now we're going to start looking at what happens when we apply a voltage on it here. So first off, we should think about when this depletion field was set up, the electrons were moving essentially from the right to the left, and so the direction of the electric field would have been in this direction to the left, when that depletion region was first formed. Okay, so what we're going to first do is we're going to look at what we call a reverse bias junction. And what that means is I'm going to apply a voltage to this, but I'm going to have it so that I'm applying a negative voltage to the P side. So if you want to think about this, if you were measuring the voltage from the P side to the N side, it would be a negative voltage that you're measuring. But the key thing here is thinking about what the direction of the electric field is here. So the direction of the electric field, because of the way this voltage is set up, the direction of the electric field would also be in, and I'll say E applied here, for the electric field being applied, would be in the same direction as the electric field that set up the diffusion, to set up that depletion region. And so what that's going to do actually is that's just going to increase my depletion region. So I'll have a larger depletion region by putting a reverse voltage on it. And now remember, you might say, well, what happens if you increase the depletion region all the way to the end of the P and N side here? Well, first off, this isn't actually how the devices are physically built. This is just a graphical representation of the PN junction. But even if you were talking about putting it all the way out to the ends of the device, it doesn't matter because remember we said that there's essentially no free electrons or holes in the depletion region. So there's no free carriers in that depletion region. So essentially that means there's essentially no current going on in that depletion region. And so that really kind of is like, okay, well, we've made the depletion region bigger. So no current is going to be flowing through there. But there is an effect that we have here, is we actually have kind of a capacitor in essence here. And what we have here is that you can look at this edge here. Well, we go back to the original black one here. You could think of, before we applied the voltage, you could think of these as being like a positive and negative plate, and you got an electric field that's been set up, and you've got negative charge on one side, positive charge on the other side, so you have a capacitor, because you can think of it as like, oh, you got a conductive plate, no currents in the middle, you've got charge built up on each side, so you got a capacitor. And what we've done here, though, by applying a voltage, is we've actually just made this capacitor bigger. And so there is something that's called the junction capacitance. And that junction capacitance is, again, because it's in a reverse bias situation. Now, to compute that is actually pretty easy. There's a pretty simple formula. It's CJ0, which we'll talk about what that is in a second. 1 plus the voltage that I've applied, so that reverse voltage that I've applied, over V built in to the -1/2 power. So it's the square root of that. And this CJ0, this is just the junction capacitance with 0 volts applied. And so, in essence, we've created a capacitor that the capacitance of the capacitor varies based off the voltage that's applied to it. And there actually are such capacitors that exist like that, and they're actually used for various applications. Now, I don't believe this is the way they manufacture those variable capacitors, but this does give us a capacitance that varies with the voltage that's applied. Now, one thing though we want to really think about here though is no current flows, because this is going to be one of the most important things here with our operation of a p-n junction or a diode, is that if you reverse bias it, in other words, if you put a negative voltage on the P terminal, it's in a reverse bias situation and no current flows. So that's important for a takeaway here. Well, you probably can guess the next thing we're going to look at is, well, what happens if you have a forward biased diode? So let me draw another diode here. Let me make it a little bit longer than what I had. P side, N side, and this is my depletion region. And now we're going to apply a positive voltage on the P terminal. And now remember, there was this kind of electric field that had been used to establish this depletion region that was going to the left here. And now the electric current is the electric field that's being generated by the voltage being applied is going in the opposite direction. So it's kind of going against that built-in voltage here. Now, what's interesting about this is that this actually, the current here is actually controlled by not the majority carriers, but the minority carrier. So what happens here? Well, at this x equals 0 spot here, we have, and I'm going to put this in red here, we have, and I'll put this one down here, n sub p 0, and actually I drew that line too far. I need to bring down my depletion region lines. And then we have this P sub N0. And this is with no voltage applied here. So we have these excess minority carriers, so these excess electrons, excess holes here, that are kind of sitting around there, and then the depletion region, there's no free carriers. That's why I have nothing in here. Now, if I apply an electric field that goes in the opposite direction of this electric field, what I'm doing here is I'm actually going to be increasing so this blue curve is going to be when I have this thing here. So I'm going to be increasing my minority carriers. So this is, I'm going to get an excess of electrons now. I draw too many arrows there. This is an excess of electrons. And similarly, I will have a similar behavior because of the electric field where I will get an excess of holes. And that's again because of the direction of the electric field. All right, so then what happens here? Well, we have a gradient in other words, slope at each point here, and the same thing over here. Well, what does that really tell us here? Well, that's telling me that the derivative of n sub p, so the electrons on the p side of the silicon with respect to x, is not equal to 0. And similarly, the derivative of p of the holes on the n side of the silicon is not equal to 0. So what that means is we have a diffusion current. And so we now have a current, and that current is flowing in this direction. The current is flowing in that direction. And so we now have current going through the device. Now you might say, well, I still have this depletion region that you told me there's no free holes or electrons, but well, what ends up happening is that we have this current here that's set up. So we got this current that's set up here, and the electrons are actually getting swept this direction and the holes are getting swept the other direction. But for easiness sake, just assume you have like a particle here and we've got a current going. And we know this particle, whatever charge this particle is, in this case it would be positive because it's going to the right, but there's current moving, so this thing's moving and it will enter the depletion region. But then you might say, well, wait, you can't have any free carriers in the depletion region. And you're right, we don't really have free carriers. But what happens is it just gets swept clear across the depletion region and gets put over to this side and then just continues its journey on, setting up this current that we call ID. And as far as I didn't label it here, but the voltage we apply we call VD, because we're going to again call this a diode. So the end story here is a PN junction we call it a diode. and PN junction called a diode. I just lost track of my thought there for a second. Don't you hate it when that happens? Oh, I know what I was going to do. I was going to draw the electrical symbol for a diode. This is the electrical symbol for the diode. Now this is the P side of the diode, and this is the N side of the diode. And there's a little line here. Now if you look at a physical diode, like one that's in the drawers, that's an axial component, so it's got little wires coming out here. There's going to be like a bar on one side of the diode here, and that indicates the N side of the diode. And so this would be the P side of the diode. Because it does matter what direction we plug diodes in when we start building circuits with them. Because if the diode is reverse biased, this means negative voltage applied to P, we have no current flow. And I'm going to actually say essentially no current flow. Technically it's not zero, but you'll see in a second that, or not in a second, you'll see in next class period that it's basically zero. And then if the diode is forward biased, positive voltage applied to P we have current flow. Now we'll talk about this in a lot more detail because this is one of the most important, as I said, it's not the only application of a diode, but one of the more important ones is that it can be used as something that's called a rectifier. And if you want to write that down in your notes, great. We're going to talk about rectifiers more, so don't worry if you don't have it in your notes right away. But it can be used as a rectifier, which is going to be a critical component for us to turn an AC voltage into a DC voltage. So that's one of the things we'll be able to use diodes for. Now there are other applications for diodes. We hopefully all know, and if we don't, that's fine, but LED stands for light emitting diode. So in that case, what you do, and there's actually a symbol for those, that case, instead of it really being used as a rectifier, when you apply a voltage, a positive voltage on it, what ends up coming out, and those two little squiggle lines there with arrows are indicating that light's coming out of that diode. And so there are lots of special purpose diodes. There's also something called a Zener diode, which we'll learn about. A Zener diode has a symbol that looks like this. And one of the interesting things about a Zener diode is it's actually designed to work backwards, which seems weird, but that's the way it's designed. And we'll go into the applications of that as well. Zener diodes can be used in voltage regulators. So there's a lot of different applications for diodes, but we will get into those in more detail. What we're going to start with next week is we're going to start with what's called the ideal diode equation, which is going to give us an equation that relates the current through the diode with respect to the voltage that's being applied to the diode. And then we'll go through some examples of that.